Most people picture extreme deserts as dunes baking near the equator, where the air is an oven and the sand holds nothing but heat. The coast of northern Chile contradicts that image entirely. Here, the average temperature hovers around a cool 18 degrees Celsius, and almost every morning, a thick rolling oceanic fog, known locally as the camanchaca, sweeps directly over the coastline. It coats the rocks and saturates the ground with a scheduled delivery of moisture. Then by noon, it quietly burns away. The moisture arrives, but it never turns into rain. Deeper inland, the earth sits cracked dry. In the core of the Atacama, average rainfall is measured in fractions of a single millimeter a year. There are weather stations here that, over their entire history of operation, have never recorded a single drop. This profound aridity, sitting directly beneath a steady supply of visible water, emerges from the overlapping gears of a perfectly engineered planetary trap. The Atacama is caught at a precise intersection of three enormous geographic machines, each independently hostile to moisture. The first machine is the atmosphere itself. Warm, wet air rises near the equator, dumps its rain, and drifts high overhead. As that air descends over northern Chile, it warms and dries out, completely suppressing the upward motion necessary to form rain clouds. The second machine is the physical walls pinning the desert in place. The Atacama is caught in a double rain shadow. Towering Andes block Atlantic moisture. Weather systems drop their water on the eastern slope, so the air spilling over the peaks is completely dry. The third machine sits in the Pacific Ocean. The Humboldt current channels frigid water from the deep south straight up the western coast of the continent, keeping the ocean surface abnormally cold. That cold water chills the marine air directly above it, making it heavy. Instead of rising to form storms, this cold air is trapped. Trapped beneath warmer air, it can only crawl inland as a dense, low-hanging fog, sinking subtropical air from above, a double mountain shadow, a cold ocean current. These overlapping forces build an inescapable vault, permanently sealed from rainfall. The South American plate has been parked under this specific atmospheric trap for roughly 150 million years. Without washing rain to dissolve and carry minerals away, they simply fade, accumulating over deep time into vast crusts of sodium nitrate, known as caliche. During the early 20th century, this extreme dryness generated a global fortune. The world rushed to mine these concentrated nitrates for explosives and fertilizer, building rail lines and boomtowns across the barren sand. When synthetic nitrogen was invented, the industry collapsed, and the workers emptied the boomtowns almost overnight. The utter lack of humidity perfectly preserved their timber and rusted iron, exactly as they left it. The desert's deep time stability easily preserved the remnants of human ambition, proving that a landscape entirely hostile to water can still dictate global geopolitics. Today, scientists utilize this harsh, oxidizing, perchlorate-rich soil for a different pursuit. Astrobiologists come to the Atacama to run direct rehearsals for exploring Mars. But the soil is not entirely dead. Microscopic extremophiles manage to survive here, hanging on to microscopic humidity and tiny buried seams of damped clay. The dirt also conceals millions of plant seeds. They lie completely dormant in the dry earth, waiting out decades of absolute drought. Every few years, an ocean phase like El Niño causes the atmospheric machinery to temporarily glitch. A delivery of 15 millimeters of rain is enough to crack open those ancient seeds, triggering an explosive biological reaction that covers the desert floor. The Atacama survives as an intricate ecosystem in suspended animation, perfectly adapted to holding its breath indefinitely. Local human populations have also learned to hack the desert's stalled moisture, targeting the dense, useless fog. By erecting large mesh fog catchers on the hillsides, they comb droplets straight from the air, providing hundreds of liters of drinking water for their communities. But this sustainable, small-scale harvesting stands in stark contrast to the massive water extraction required for the modern industrial boom. The salt flats hold massive deposits of lithium brine. This mineral-rich liquid must be pumped from deep underground and then spread across immense ponds to evaporate in the relentless sun. Producing a single ton of lithium can consume 500,000 gallons of ancient water, pulling heavily from a place that has none to spare. Indigenous communities bear the direct cost. As the pumping continues, the ancient oases, lagoons, and pastures they have relied on for centuries steadily dry out. The very landscape powering the global green energy transition is draining the microscopic margins of water that allow its own life to exist. Absolute emptiness is an illusion. The driest place on Earth is simply a landscape where life, wealth, and water have spent millions of years waiting to be found.